In this section, we're going to take a look at solving trigonometric equations. So remember, whenever you're solving an equation, what you're looking for is the number or set of numbers, which, when substituted into your equation, gives you a true statement. So let's see, go ahead and recall the definition. A solution to an equation, and that's the word we're defining solution. A solution to an equation is a number or a set of numbers, it can be more than one, a set of numbers that, when substituted into the equation, makes a true statement. All right. Now, we have several techniques for solving equations. Going back to algebra, essentially, you're trying to isolate your variable. If you think back to just basic algebra, if you have an equation like 2x plus 5 is equal to 17, you can isolate your variable. You can subtract the 5 from both sides, gives you 2x equals to 12, and then dividing both sides by 2 isolates your variable. You have your x equals to 6. Once you isolate your variable, that value is your solution. You can always check this, of course, because you can always take this number and substitute back into your equation. This x is said to be the number 6. Now let's see what happens if we plug in 6. 2 times 6 would give me 12 plus 5. And now 12 plus 5 is 17. Well, that's what we were supposed to get. 2x plus 5 equals 17. And if you plug the number 6 in there, that in fact does give you 17. All right, so now what do we mean by trigonometric equations? Well, a trigonometric equation is what it sounds like. It's an equation where one or more terms involves a trigonometric expression, either sine, cosine, tangent, secant, cosecant, or cotangent. The techniques that you learn in algebra do not go away. Rather, we're going to build on them. This is still going to be a valid technique, isolating a variable. The difference is now, instead of isolating a variable from a polynomial equation, we're going to isolate a variable in a trigonometric equation, something where instead of 2x plus 5, we might start off with something like 2 times the cosine of x plus 5, or 2 times the sine of x plus 5 times the cosine of x, or something along those lines. The way we solve a trigonometric equation depends on what pattern it fits. Well, what are the patterns? Well, let's take a look. The simplest case is one in which you have just a single trigonometric expression and everything else is just a constant. No other variables, no other numbers, just one trigonometric expression, and everything else is just a regular number. This is the most like a linear equation. It's not exactly a linear equation because you can't just get the x by itself by adding or subtracting, because the cosine of x can't be isolated. You can't isolate your x by just adding or subtracting something here. But even though we can't isolate x, we can isolate the cosine of x. So you'll notice this looks very similar to the previous problem, at least until the end, because here, if we add 1 to both sides, that'll give us 2 cosine of x is equal to 1. And if I now divide on both sides by 2, this gives me the cosine of x equals to 1/2. Well, now we can think of the number off of our unit circle. Remember what our unit circle looks like. There's a few places where the cosine of x is equal to 1/2. Okay, well, the cosine of x is equal to 1/2. That would be here and here. where the angle is pi over 3, and this would be 5 pi over 3. So you notice there's two locations where that happens. Well, at this point you think, well, wait a minute, aren't there more? I mean, there's pi over 3, but if I go all the way around the circle, don't I get another solution? Wouldn't that be 2 pi over 3? Wouldn't that be 2 pi plus pi over 3? That's 7 pi over 3. Wouldn't that work also? And yeah, actually, if we check it, 7 pi over 3, if I take its cosine, that's also a half. And if I go all the way around the circle again, that'll be 4 pi plus pi over 3. Wouldn't that work also? Yeah, so that does keep working. So whenever you solve a trigonometric equation, one of two things has to happen. Either we have to know where we want our solutions. In an application, that would become apparent based off of the application. But this being a math class, we're not going to see too many applications. For the most part here, if your solutions are supposed to be in some interval, we'll tell you, hey, look for the solutions where x are in between 0 and 2 pi, or x is between 0 and 4 pi, or whatever. But if we're not given an interval, if you're not told, hey, you need your solutions between here and here, then there's going to be an infinite number of solutions, because every time you go around, you get another solution. When I say, well, if there's an infinite number, how am I ever going to find them all? Well, there's an infinite number, but they all fall into one of two categories. They're either going to be this number, around and around and around, or they're going to be this number after I go around and around and around. So the way we do it is we look on the unit circle and we find what are the solutions here. Okay, well, from just the unit circle, I find that x equals to pi over 3 and x equals to 5 pi over 3. Okay, so those are two solutions. And if you plug them in here, that'll actually make that work. But there's a bunch of others. Well, yeah, but the way I find another one is if I start at pi over 3, if I add 2 pi, that gets me another one. If I add 4 pi, that gets me another one. 6 pi, 8 pi, 10 pi. Every time I add another 2 pi, I get another answer. So that's how we're going to write it. We're going to say every one of these answers is pi over 3 plus, either 2 pi or 4 pi or 6 pi or 8 pi. The way we write that so that we don't have to write out a giant list is we write it as 2n pi. Here, this n represents any integer. If you pick any integer, say for example I pick the number 1, well that's 2 times 1 times pi. Okay, so pi over 3 plus 2 pi. Hey, yeah, that works. If I pick n is equal to 5, well then that's 5 times 2 is 10 pi. Well yeah, but if I start at pi over 3 and I go around 10 pi units, 10 pi radians, I end up right back there. And so that's a solution. So anytime you have an infinite number of solutions like this, you don't actually need to write an infinite number of things. It's just this point and a whole bunch of other points that are found by rotating around the circle as many times as you need to. Same thing for this one. Here, if my 5 pi over 3 is a solution, then all my other solutions are going to be 5 pi over 3 plus some multiple of 2 pi. So we can write that as 2n pi. And there we go. We have an infinite number of solutions, but they all fall into these two families of solutions. And there we go. So now here is another example. Consider 3 times the tangent of x plus 3 is equal to 0. This is going to work in a similar way to this one. So right now, you should pause the video and give this one a try. Once you've got an answer, go ahead and unpause the video and we can go through it together. All right, well, we can begin by isolating the trig function, the tangent of x. All right, well, let's subtract 3 from both sides. That makes that go away. And that will give us 3 tangent of x is equal to negative 3. Next, we can go ahead and divide both sides by 3. 3 divides 3 to give me 1. And now I'm left with the tangent of x is equal to minus 1. Now, one way we can think of this is off the unit circle. But remember, we do have other resources for helping us visualize our trig functions. In particular, we can take a look at the graphs of the trig functions. We're not restricted to just the unit circle, although for sine and cosine especially, it is useful. We could also think about the graph of the tangent function. We spent a whole chapter talking about graphs. Why not use those? Remember what the graph of the tangent function looks like. It crosses through the origin, it goes up to the right, and it has an asymptote here at x equals pi over 2. And then it goes down to the left, and again I have another asymptote at x equals negative pi over 2. Now remember, that's just one period of my function. This does keep going forever and ever in both directions. So here I would have another period from here to here. If I subtract these two numbers, I get pi. That's the distance across one period of tangent. So if I subtract these two, that would be another pi. So pi over 2 plus the other pi would make this asymptote 3 pi over 2. Like that. And so forth and so on. And it just keeps on going. All right? Now, on this graph, it becomes apparent that my central period of tangent is equal to -1 at, well, just this one spot right here. And here, that's going to be negative pi over 4, comma -1. And we can check that. The tangent of negative pi over 4, that's the sine of negative pi over 4 over the cosine of negative pi over 4. Right? The tangent of negative pi over 4 is the sine of negative pi over 4 over the cosine of negative pi over 4. That's the same as saying negative root 2 over 2 over root 2 over 2. And a negative number over the positive version of itself, well, that's just going to be -1. So yeah, that does work out. Negative pi over 4 works out. Okay, so I know one of my solutions is negative pi over 4. Oh. But now, looking at this graph, it becomes apparent that that's not the only solution. There's another one here. And if I were to draw more periods of the tangent function, there'd be another one here, and so forth and so on. But notice, that's just from here, evenly spaced. Well, we know that the period of the tangent function is pi. So if I'm at this point, if I add pi radians, I'm at this point. If I add another pi, I'm at this point. Okay, so here, that negative pi over 4 is the solution in my central period. It's the only one. But I can find a bunch of others if I add copies of pi. If I add 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. The way we do that is we add n pi. Notice here, if your function has a period of 2 pi, to find other solutions, you add 2n pi. But if your period is length pi, well, then you just add n pi. And this right here, even though it is written as a single equation, is an entire family of solutions. There's a whole bunch of solutions that all satisfy this equation. So now that works out pretty well, but not every kind of equation is going to look like this. Just like not every algebraic equation is linear, not every trigonometric equation will look quite like this. Let's consider now something a little bit bigger. So here the question is still the same. We're supposed to solve. In fact, that's going to be the question for every one of the problems for the next couple of sections. We're going to solve something. All right. Let's go ahead and solve the equation 2 times the sine squared of x plus the sine of x minus 1 is equal to 0. All right. Now, here, what we want to do is we want to recognize that this looks a lot like a polynomial equation. In particular, notice that this looks like that's 2. I'm not going to use x here because here that might get confused for this x. I'll use a different letter. I'll say 2u squared plus u minus 1 is equal to 0. This looks like 2 times something squared plus that same something minus 1. 2 times something squared plus that same something minus 1. Well, now that we know how to solve. We could factor that one. Here, this factors out as 2u minus 1 and u plus 1 is equal to 0. At this point, you could now set each of these factors equal to 0 and solve. Right? Well, notice that since it has that same pattern, that means we can do the same thing to this kind of an expression. Right? Notice that if this is 2 something squared plus something minus 1, that can be written as 2 times that something minus 1 times that something plus 1. Well, notice that something is the sine of x. So I could do the same thing over here. I could write this as 2 times the sine of x minus 1 times the sine of x plus 1 is equal to 0. Okay. Note what that is basically substitution. In college algebra, you learn the technique of substitution to help you factor things. And that is to say, if something fits the pattern of a polynomial, you can take the bigger piece and call it some other letter. U is a common choice, but you can use anything you like. But then once it's a polynomial with just a letter, like u, you could factor that. That factorization will tell you what to do to your bigger original problem. But notice now, this times this is equal to 0. Oh, well that means this one can equal to 0. And separately, this one can equal to 0. So let's give that a try. Here, this splits into two different equations. We can now split this as 2 times the sine of x minus 1 equals to 0. And separately, the sine of x plus 1 is equal to 0. Each of these can now be solved just like we solved the first set of problems. You can add the 1 to the other side, giving you 2 times the sine of x is equal to 1, and then divide both sides by 2. And that's a half. On this side, I can subtract 1 to the other side, and I get sine of x equals minus a half. So now I've isolated the sine of x. I've isolated the trig expression. So what I want to do now is I can take these expressions and I can solve for x. Since this is the sine function, the unit circle should be fairly handy. But if you want to use the sine function's graph, the sinusoidal graph, that's fine too. All right? So we can now take these and we can solve. Here I'll go ahead and use the unit circle, but that's just a personal preference. With sine and cosine, I'd rather use the unit circle. We could use the graph of sine, the wave. But here, the unit circle is enough for me to see that if I want the sine of x to equal to 1/2, well, that's going to be here and here, which is pi over 6 and 5 pi over 6. At both of these locations, I have the sine value is equal to 1/2. If I want the sine of x to equal to -1, well, the sine of x equals to -1 only at one place on the unit circle, and that's down here. That's at 3 pi over 2. All right, so those are my solutions. Here I have x is equal to, it can either equal to pi over 6 to solve this part, and here x can equal to 5 pi over 6, also solves this part, and over here x equals to 3 pi over 2 is the solution to this part. But now, again, we haven't been told to stop, to say, oh, we only want the solutions between here and here. We want all the solutions. So here, these are only the solutions on the unit circle. If we want all the solutions, well, sine has a period of 2 pi. So we're going to add 2n pi to each of these. so that they can give us every possible solution that can exist. So here we have an infinite number of solutions, but they all fit into one of these three families. Just like that. All right, so let's take a look at another example. Here, we need to solve the equation cosine squared of x is equal to 3 minus 2 times the cosine of x. Oh, okay. So you look at this one and you say, well, okay, now that looks really different from some of the other problems we've done. So far, all of our problems have had something equal to 0. All right, this is equal to 0, and this was equal to 0, and this was equal to 0. Oh, okay, well then let's just move everything over. There's no reason why this has to be any different. So let's just go ahead and move this stuff over. So here we can write this as cosine squared of x. Let me add 2 cosine of x to this side. And let me subtract 3 over here. So now all the stuff's on one side, the other side's equal to 0. So at this point, go ahead and give this a try. You should pause the video, and once you have an answer, go ahead and unpause and we'll go through it together. All right, so let's take a look. Here, this can really be treated like u squared plus 2 times u minus 3 equals to 0. Okay, but that would factor out as u minus 1 and u plus 3. Okay, so this would factor out as, here notice that you're saying that u is the cosine of x. So here, this u and this u would be the cosine of x. So this factors as the cosine of x minus 1 and the cosine of x plus 3 equals to 0. All right, so now we have the product of two things is equal to 0, which means we can set each of them equal to 0. All right, so let's give that a try. If I set each of these equal to 0, I get the cosine of x minus 1 equals to 0. Over here, I get the cosine of x plus 3 equals to 0. I can now add the 1 over to this side here. So this will give me the cosine of x is equal to 1. And here I can subtract the 3 over to the other side. And that would give me cosine of x equals to negative 3. Notice that's not possible. Remember that the domain and the range of, that the domain of the cosine function is infinite, but the range of the cosine function is only from negative 1 to 1. I can't take the cosine of a number and get negative 3. So here, this cannot happen. Okay, so if that can't happen, then that means there's no solution. Well, okay, there's no solution to this part. What about this? Oh, well, this one we can do. The cosine of x is equal to 1, and there's, on the unit circle, the place where the cosine of x is equal to 1 is right here. That's 0. So here, x is equal to 0. Oh, but again, we don't have any restriction. We're not told, oh, the answers have to be between here and here. So for this one, we say, okay, that's 0. But if we go around and around and around, every time we go around, we get a new solution. So remember, the cosine function has a period of 2 pi. So to get every possible solution, we can write plus 2n pi. And here, since adding something to 0 doesn't change that something, well, here we can even write this a simpler way. We don't need to write the 0. We can just write this as x is equal to 2n pi. And that is our set of solutions. Now the next thing we want to look at, this is going to be another one that's going to start off similar, but somewhere in the middle, something a little different is going to happen. All right, so let's say I have the tangent squared of x plus 4 times the tangent of x plus 2 is equal to 0. Okay, this looks just like all the previous ones. In fact, oh, and here I should give some direction. This is solve. And in fact, well, I can think of this as u squared plus 4 times u plus 2 is equal to 0. All right? Because here I'm thinking of tangent of x as being my u. So that's u squared plus 4 times u plus 2. But when I write it like that, it becomes a little apparent that I don't know what to do with that. I don't know how to factor that. What two numbers multiply to give me 2 and add up to give me 4? There aren't any, at least not that I can think of. But factoring is not the only way that we can solve a quadratic equation. We also have the quadratic formula. Here we can say u is equal to negative b plus or minus the square root of b squared minus 4 times a times c, all of that divided by double the value of a. So this will give us negative 4 plus or minus the square root. 4 squared is 16 minus 4 times 1 is 4 times 2 is 8. Your denominator, 2 times 1 is 2. Okay, so that's going to be negative 4 plus or minus the square root of 8 over 2. Now notice, the square root of 8 can be simplified. We can write this as negative 4 plus or minus 2 root 2 over 2. And finally, each of these can be divided. Negative 4 divided by 2, well, that's negative 2. And here, 2 root 2 divided by 2, that just leaves me the plus or minus root 2. So here, that means u is equal to that. But remember, u is taking the place of tangent. So if u is equal to this, then that means up here I can say tangent is equal to this. And you say, well, what do you mean this? There's two things here. Well, yeah, okay. There's two different solutions. U can equal to negative 2 plus the square root and negative 2 minus the square root. So up here, tangent of x can equal to negative 2 plus the square root of 2. And tangent of x can equal to negative 2 minus root 2. Here we won't have any problems like we did up here. Cosine has a range from minus 1 to 1. If you remember, tangent doesn't have that restriction. The graph of a tangent function goes on forever, up and down. So here, tangent of x can be literally anything. It'll go up forever and down forever, hitting every number. But now the question is, well, what is that? The tangent of x is equal to negative 2 plus root 2. On the unit circle or on my graph, I don't know what that is. I can't think of one. Well, that's okay, because after all, we saw in a previous section the inverse trig functions, which say that if I take the inverse tangent of a tangent of x, that'll just give me x, so long as everything's in the proper domain. All right? So here, I can go ahead and say, well, I want the tangent inverse of both sides. So here I want the inverse tangent of the tangent of x, just like that, is equal to the inverse tangent of negative 2 plus root 2. Here, the inverse tangent of the tangent of x, that's just going to give me x. Here, this is going to be the inverse tangent of negative 2 plus root 2. And there we go. Same thing is true over here. If I take the inverse tangent of both sides, I can get x by itself is equal to the inverse tangent of negative 2 plus root 2. Just like that. Now keep in mind, these solutions repeat. The period length of a tangent function is going to be pi. So every time I add a copy of pi, this will provide another solution. So here we shouldn't leave these like this. This really tells us that the solutions fall into a family. Here, the family is the inverse tangent of negative 2 plus root 2 plus n pi. And over here, I get that x is equal to the inverse tangent of negative 2 plus root 2. Oh, my apologies. That should be, I should have one of these plus and one of these minus. I wrote them both as plus, right? Plus or minus, plus or minus. So this should be the inverse tangent of negative 2 minus root 2, and again, plus n pi. So that gives us our family of solutions. At this point, you may be tempted to go grab a calculator and say, okay, what is the inverse tangent of negative 2 plus root 2? Well, there it is. That's the number. After all, if I say my answer is the square root of 2, I'm not particularly compelled to grab a calculator for that. Square root of 2 is just square root of 2. Yeah, if I grab a calculator, I happen to have one of those right here, I could take the square root of 2 and I'd get some decimal approximation. But notice that's not actually the answer. You say, yeah, it is. Look, you took the square root of 2. Well, yeah, but the calculator has a limitation. It runs out of space right here. This answer is actually longer. It keeps on going. So here, this is an approximation. It's not actually the square root of 2. It's just about the square root of 2, more or less. Same thing with this. Right here, if I come over here and I type in negative 2, and then I add the square root of 2, well, first of all, that square root of 2 itself is an approximation. But now if I take the inverse tangent of that, that's another number, which is not correct. It's about right, but it's not exactly correct. So here, this is actually a more precise solution. This is called an exact solution. We've seen things like this before, so let's remind ourselves of what that means. An exact solution is one that isn't rounded. It isn't more or less. It's not about. Right? It isn't a very good approximation. It is exactly the correct answer. So here, not only is this an okay answer, it's actually better than what you would get out of a calculator. And so as far as we're concerned, this is what we're going to want to have. All right? So now, our next example, let's take a look at a problem like this. This will work similar to what some of the problems we've seen, but so far, all of our examples have either had a single trig function, either a single sine, or a single cosine, or a single tangent, or if you have multiple copies of things, it'll have different versions of the same function. Sine, sine squared. Cosine, cosine squared. Tangent, tangent squared. What if I don't have the same kind of function? Or rather, what if I don't have the same kind of expression within my equation? So let's say, for example, I began with something like cosine squared of theta is equal to sine squared of theta plus 1. Looks like that. Well, the nice thing about trig functions is that every trig function can be written in terms of every other trig function. If you have a function that involves sine of x, if you're careful, you can write it as cosine or tangent or secant or cosecant or cotangent. Every trig function is interchangeable with every other trig function as long as you use the right identity. Here, this is different from every problem we've seen so far because now we have two different trig functions. But that doesn't have to be like that. We can take this sine squared of x, and by using the Pythagorean identity, we can write it as 1 minus cosine squared of x. And because that is now no longer using sine, because it's now using cosine, now this looks just like all of our previous problems. So recall the Pythagorean identity. This is the single most used identity in all of trigonometry, and it's a single most used identity outside of trigonometry. So this is definitely the one you want to remember at a moment's notice here. So the cosine squared of x plus the sine squared of x is equal to 1, which means if I subtract the cosine squared of x to this side, I get sine squared of x equals 1 minus cosine squared of x. And I'll be using that right here because I'll take this sine squared of x and I'll replace it with 1 minus cosine squared of x. So I get cosine squared of theta right here. That's going to stay the same. But here, instead of sine squared of something, I'm going to have 1 minus the cosine squared of that something. Here I'm using theta instead of x. Okay, that's fine. So here I'm going to write this as 1 minus cosine squared of theta, and then plus 1. That plus 1 stays, that cosine squared of theta stays, but here these two are changed one for the other. All right, but now things are a lot simpler. Here, let me go ahead and combine some like terms. Here I have a 1 and a 1. All right, well, that'll give me 2. So that's cosine squared of theta is equal to 1 plus 1. That'll give me 2. The minus cosine squared of theta has stayed there. But now let me add that over to the other side to make things a little bit nicer. Cosine squared of theta gets added over here. That all is gone. And we're left with double cosine squared of theta is equal to 2. I can isolate that cosine squared of theta if I divide both sides by 2. 2 divided by 2 is 1, which is what I want. I want 1 cosine squared of theta. Here, 2 divided by 2 is 1. Here, just for the sake of illustration, the question is to solve. In all of our examples so far, we've wanted to solve for every possible answer. Here, let's solve in the interval from 0 to, let's say from 0 to 2 pi. So here, we're putting a little restriction on it. If this was an application problem, if you were doing this in the context of building something, measuring something, if you were doing stellar cartography, if you were doing some topography or something that involved trigonometry, some surveying, then this would come from the restrictions of the real world. But this is purely computational. This is purely theoretical. We don't have any application at this point. So here, if we're going to give you a restriction, we just have to give it to you. We tell you, hey, make sure your answers are somewhere between here and here. You'll notice that here we will not get an infinite number of answers because we only want the ones in this small interval. All right, so let's continue here. I'm going to take the cosine squared of theta is equal to 1. I don't want cosine squared of theta. I just want cosine of theta. So let me get rid of that square by taking the square root. Now remember, when you take a square root, there are two different square roots. There's a positive root and a negative root. So here we're going to get two different results. The cosine of theta is equal to plus or minus 1, which gives me two different kinds of answers. Cosine of theta is equal to 1, and cosine of theta is equal to minus 1, plus or minus 1. All right, so there we go. We're going to get just a few solutions. Looking at our unit circle, I find that the cosine of an angle is equal to 1. Well, that's going to happen right here. And the sine of an angle is equal to negative 1. The cosine of an angle is equal to negative 1. I said sine, didn't I? So cosine of theta is equal to 1. That happens at 0. It would also happen at 2 pi. Here, cosine of theta is equal to negative 1. That would happen at pi. Oh, but notice, I only want the answers between 0 and 2 pi. I'm okay with 0, but I'm not trying to include 2 pi. Okay, so on the unit circle, I found 3 answers. Oh yeah, but this one is outside of the region that I want. It's outside of the interval that I'm looking at. So here, this is not in here. So even though it is a solution, it's not one that I'm going to accept. I'm only accepting the ones between 0 and 2 pi. It's okay if it's 0, but not 2 pi. So here we get two solutions. Theta is equal to 0, and theta is equal to pi. And that's it. No plus n pi or 2n pi or anything of that nature, because we're not getting an infinite number of solutions. We're getting just those two. And finally, for this section, let's take a look at this last example. Let's consider 2 sine of theta is equal to 1 minus double the cosine of theta. Just like that. Okay, well, this looks very similar to this problem up here, except that without the squares, I can't use the Pythagorean identity. Okay, so here, these are different. I don't want them to be different. I want them to be the same. That makes problems easier. Okay, so I want to change one into the other, either sine into cosine or cosine into sine. But without a square on either of these, I can't use that identity. So my choices are either find a different identity or put the squares in myself. Here, that second choice is not a bad choice. Let me square both sides. Now here's a common mistake. You do not square this and this. You square the whole thing. What I mean by that is you don't square this one and then separately square this one. It's everything is squared. You say, well, what's the difference? Remember how squaring works. 1 minus 2 cosine of theta squared means 1 minus 2 cosine of theta times 1 minus 2 cosine of theta. And when you multiply something like this, you're going to distribute. 1 times 1 makes 1. 1 times minus 2 cosine of theta is minus 2 cosine of theta. Another minus 2 cosine of theta times 1 is another minus 2 cosine of theta. And negative 2 cosine of theta times another negative 2 cosine of theta. Double negative makes that a positive. 2 times 2 makes 4. Cosine of theta times cosine of theta is cosine squared of theta. I can combine those like terms, and that'll give me 1 minus 4 cosine of theta plus 4 cosine squared of theta. Notice, you don't just square the 1 to give me a 1, and you don't just square the cosine to give me cosine squared of theta. Here, you multiply everything out, which gives you more terms than just squaring each one. That is a very common mistake, so don't be the one who makes it. You don't square each of these, you square the whole thing, which means you distribute. This one doesn't have any worries because here there's only a single term. Here, the reason I need to distribute is because I have a binomial times a binomial, 2 terms and 2 terms. Here, there's only 1 term, right? There's no plus or minus in between these, so they're all the same term. So this one, I can just square each piece. Note, multiplication, I can square each piece. Addition or subtraction, I have to distribute. All right, so here we go. Here, this is going to give me 4. This is sine squared of theta. This, well, that's all of that stuff. That's going to be 1 minus 4 cosine of theta plus 4 cosine squared of theta. Just like that. All right, well, I have 2 of these that are cosines, and one of this is a sine. Okay, so I should probably change this one. Could I change all the other ones? Yeah, maybe, but here there's only one thing to change, so it'll be easier to work with this one. So, using my Pythagorean identity, cosine squared of theta is sine squared of theta is equal to 1 minus cosine squared of theta. So here I can write this as 4 times, instead of sine squared of theta, I'll write as 1 minus cosine squared of theta equals 1 minus 4 cosine of theta plus 4 cosine squared of theta. I haven't changed anything on this side. I've only changed this via the Pythagorean identity. All right, I can distribute that 4 now. 4 times 1 is 4. 4 times negative cosine squared of theta is negative 4 cosine squared of theta is equal to 1 minus 4 cosine of theta plus 4 cosine squared of theta. Let me make one side equal to 0. This now looks promising. I have only cosine and cosine squared. Let me get everything together so I can combine my like terms. Let me subtract 4 from both sides, and add 4 cosine squared of theta to both sides. 4 minus 4 is 0. 4 cosine squared of theta minus 4 cosine squared of theta is also 0. And so now we're left with 0 here. Here I'm going to write this in descending order. Biggest power first. 4 plus 4 will give me 8 cosine squared of theta. That one doesn't have anything to combine with, so I'll leave that as minus 4 cosine of theta. And then 1 minus 4, that'll give me a negative 3. We can now take this, and using some substitution, we can think of this as a polynomial equation. All right, so let's think of this like this. It's going to be 0 equals to 8u squared minus 4u minus 3. And that doesn't look very friendly. Doesn't look like factoring is going to be an easy option. So maybe the quadratic formula. At this point, pause the video and see if you can finish this off yourself. See if you can get to the solution. Remember, we're looking for all possible solutions here, so there's no restriction, which means you are going to find not individual answers, but a family of answers. So pause the video, see if you can finish this yourself, and once you're ready, go ahead and unpause and we'll go through it together. All right, so let's take a look now. We can use the quadratic formula for this one. Here, u is equal to negative b plus or minus the square root of b squared minus 4 times this a, which is the number 8, times c, which is negative 3, all over double the value of a, which is the number 8. Here, double negative makes that a positive, positive 4, plus or minus the square root. Negative 4 squared is 16. Here, these are both negatives. Negative 4 and negative 3 make positive 12. Positive 12 times 8 is positive 96. And our denominator, 2 times 8, is 16. You can add those together, and that would give you plus or minus the square root of 112 over 16. But now this can be factored out some more. After all, the square root of 112 can be written as, here I'm going to write 4 plus or minus. This is going to be 4 root 7 over 16. And here, I can divide out the numerator and the denominator by 4. So that'll give me that u is equal to, let's see, if I divide this all by 4, I'm left with 1 plus or minus root 7 on the top, and on the bottom, I get just the number 4. So I found the value of u, but remember, u is the cosine of theta, right? Here, 4 cosine of theta was 4u, which means the cosine of theta represents the u. So here we get that the cosine of theta is equal to, and I have two possibilities. I have 1 plus the square root of 7 over 4. And I have the cosine of theta is equal to 1 minus the square root of 7 over 4. Just like that. Now before we proceed, we got to make sure that these are valid. Remember, there are times where you're going to get a solution, or rather, you're going to get a part of your problem which doesn't have a solution. For example, earlier, we saw here where we got to this part of a problem where we said, okay, our solutions are, well, we want whatever makes cosine of x equal to negative 3. And that just couldn't happen. Because remember, the answers to the cosine of x have to be between minus 1 and 1. The range of the cosine function is between minus 1 and 1. Here, we need to check to make sure that those are between minus 1 and 1. If this is bigger than minus 1, or sorry, if this is bigger than 1 or less than minus 1, or this one, well then these aren't valid. Okay, here you could pull out a calculator, but it's not really necessary. We just need to know more or less what these are. Square root of 7 is 2 point something, plus 1 is 3 point something. 3 point something divided by 4, that's a positive point something. Okay, yeah, that's between minus 1 and 1. Same thing here. The square root of 7 is 2 point something. It's not quite 3, because the square root of 9 would be 3. The square root of 7 is a little bit less. so 2 point something. 1 minus 2 point something is negative 1 point something. And negative 1 point something divided by 4, well, that's a negative point something. It's about a negative a quarter, more or less. And again, it doesn't matter exactly what it is. Just I know that that number, about negative 1/4, give or take, will be somewhere between negative 1 and positive 1. So yeah, this is perfectly valid. Now, if both of those are perfectly valid, that means I can now proceed to solve for both. Here, I can take the inverse cosine. That'll give me theta is equal to the inverse cosine of 1 plus root 7 over 4. If you want to punch that into a calculator, I suppose you could, but that is an exact solution. This is better than anything that a calculator could give you, because the calculator would give you an approximation. This is exactly the answer. Likewise, over here, I could take the inverse cosine of both sides, and that will give me theta equals to the inverse cosine of 1 minus root 7 over 4, just like that. And finally, don't forget, here we didn't have any restriction on what our solutions could be. We didn't say anything about, oh, between 0 and pi or anything like that. Here we just said we want any solutions. So the period of the cosine function is 2 pi, which means if this is a solution, then any time I add 2 pi to this, it'll also be a solution. And same thing here. If this is a solution to my equation, anytime I add 2 pi, it'll also be a solution. So here I have two families of solutions. They're going to be this plus any multiple of 2 pi, or same thing over here, this plus any multiple of 2 pi. And so here I have two families of solutions, and that gives me my results. Let's take, for example, I'm going to solve the equation. And this one, I'm going to go ahead and solve it just in the interval from 0 to 2 pi. Remember, if you're not given an interval, that means you want all solutions. But given an interval, we mean we only want the solutions that fall in here. The equation we're going to solve is 2 times the cosine of 2x is equal to negative 1. Right? Now here, we're still trying to isolate the trigonometric expression. We're still going to isolate the cosine of something. But notice that our argument is different than just the normal x or just the normal theta. Now, what we do with this argument depends on what else is in the problem. If this is the only argument around, either because it appears only on its own or because there are other variables that appear, but they're also the same, if we had another 2x over here, another 2x over here, then we handle it one way. But if we happen to have more than one different kind of argument, a 2x here, a 3x here, a 5x here, then we would handle it differently. So here, this will be the simpler case, when you only have one type of argument around. If this happens, first we're going to isolate our trigonometric expression. Here, it doesn't take much. We're simply going to divide by 2. And if we divide by 2, that is now cosine of 2x equals negative 1/2. 2x, like that. Okay, so now this, the cosine of something is equal to negative 1/2. Forget about the fact that that's 2x. Just think of it as a something. Here, it might help if we actually write it with a substitution. Here, I'm going to say let every instance of 2x be written as the letter u. Right? We don't have to write it this way as long as you can keep this straight, but certainly for the first example or two, it might be a useful thing to write it this way. Here, I can write this now as the cosine of u equals to negative 1/2. Oh, well, now this looks just like one of the problems we had in the previous section, where the cosine of u is equal to negative 1/2. Well, I can visualize my unit circle. I can imagine this. And there are a couple of places where I know that I get cosine to be negative 1/2. I can have the cosine of 2 pi over 3, and that'll be negative 1/2. And I can do 4 pi over 3, and that'll be negative 1/2. All right, so here I get that u is equal to, let's see here, that's 2 pi over 3, and u is equal to 4 pi over 3. Okay? But now you say, well, wait a minute, you solved for u. Weren't you trying to solve for x? Well, that's true. But notice, u is not something completely different. U is double the value of x. Right here, what I'm going to do is, I'm going to go ahead and form these families of solutions. I'm going to say this is plus 2n pi, and same thing over here, I'll say that's plus 2n pi. Again, the period of the cosine function is 2 pi, so I'll add 2n pi. Now at this point, you might say, well, wait a minute, why'd you do that for? You only want the answers between 0 and 2 pi. Here, these are the only ones in the unit circle. Well, yes, these are the only ones in the unit circle for u. But remember, we're not trying to solve for u. We're trying to solve for 2x. Or rather, we're trying to solve for x. Remember that u is the same as 2x. So right here, when we say u is equal to this stuff, that's the same as saying 2x is equal to this stuff. And over here, when I say u is equal to that stuff, that's the same as saying 2x is equal to that stuff. But now, if I want to solve for x, which I do, I'm trying to find the value of x, I can divide both sides by 2. Okay, so let me divide by 2 right here. And then this would also get divided by 2. And this would get divided by 2. And I would do the same thing on this one. I would divide everything by 2. Well, now if I divide this by 2, I get x. If I divide 2 pi over 3 by 2, I get 1 pi over 3. And here, if I divide 2n pi over 2, I just get n pi. On this side, if I divide, I get x. Here, 4 pi over 3 divided by 2, well, that will leave me 2 pi over 3. And if I divide these 2's out, I just get n pi, just like that. And you say, okay, so you're done. But what does that have to do with what are these for? After all, you said you only wanted the answers between 0 and 2 pi. Well, so here's the thing. These two solutions were the only ones between 0 and 2 pi because they're the only ones that fit on the unit circle. But to solve for x, we divided everything by 2. That means all of our angles have gotten smaller, which means there might now be more that fit on the unit circle. Some of them would have been solutions, but they didn't fit. They didn't fit in the interval between 0 and 2 pi. But now that everything's been divided out to be made smaller, now some of them that were too big before might now fit. So here, let's go ahead and test that. I'm going to go ahead and just plug in a few numbers for n. Remember, n is an integer. So I'm going to start with the smallest integer. I'm going to start with a 0. I was going to say the smallest integer, but I guess there is no smallest integer. I go on forever in both directions. Here I'm going to start with 0. All right, so if n is equal to 0, I get x is equal to pi over 3 plus 0. Okay, and over here I get x is equal to 2 pi over 3 plus 0. Oh, well, yeah, those are definitely between 0 and 2 pi. Okay, so both of those are solutions. Let's keep going. Let's say n is equal to 1. Okay, well then that would be that would be pi over 3. N is 1, so that would be plus 1 pi. And if I take 1 pi plus pi over 3, I get 4 pi over 3. Hey, you know, that's also between 0 and 2 pi. So that is also a solution. Let's say what happens if I did that over here. I would do 2 pi over 3 plus, well now n is equal to 1, so that would be plus 1 pi. And if I do that, pi plus 2 pi over 3, that is 5 pi over 3. Oh, look, I have 1, 2, 3, 4 solutions. Let's keep going. Maybe we can find more. If n is equal to 2, well, that's going to be x equals pi over 3. If n is equal to 2, that's 2 times pi. 2 pi. Oh, but that's already too big because we want something between 0 and 2 pi. This is 2 pi plus something. Oh, that's going to be bigger than 2 pi. So here, that one's not going to work. And same thing over here. X is equal to 2 pi over 3 plus 2 pi. And again, that's 2 pi plus something. That's going to be too big. That's going to stop working. Generally, what's going to happen is here, however many solutions we had, here I had 2 solutions. Here, I cut everything in half. That's going to double my solutions, double the number. I went from having 2 to having 4. Generally speaking, whatever this number is, that tells you how many times you'll have these solutions. Or in other words, if here I had 5 solutions, and this was the number 2, I would end up with 10 solutions at the end. If I had 3 solutions for u, then after I divided by 2, that would end up with 6 solutions. Right? So generally speaking, however many solutions you get for u at this stage, you're going to multiply by that number, and that'll tell you how many solutions you should get over here. If you don't remember that, well, then you can just look for all of them and see which ones you get. But this helps a lot to help you figure out, oh, now I'm done. I know I should have had 4. I found 4, and we're good. All right? Note here that the other way you can tell is, of course, if I'm going from 0 to 2 pi, if this is n pi, I know I'm going to stop once this hits 2, because 2 pi plus anything would be bigger than 2 pi. So 0, pi, okay, that's fine. 1 pi, that's fine. 2 pi, oh, I'm done. All right? So there's a couple ways you can tell. But even if you don't remember those here, you can still just find solutions until you stop, until none of them work anymore. And so we get our results. Here our solution is x is equal to pi over 3. X is equal to 4 pi over 3. X is equal to 2 pi over 3. And x is equal to 5 pi over 3. Oops, I didn't mean to divide the x there. Just like that. And that is our solution. So now let's go ahead and look at another one. Same kind of example. Let's say we have 3 times the tangent of 3x equals to the square root of 3. And here we're going to solve. Notice here I'm not asking for a solution between 0 and 2 pi. Here I'm just asking for any and all possible solutions. So go ahead and give this a try. Go ahead and pause the video, and when you've reached a solution, go ahead and unpause, and we'll go through it together. All right, so let's take a look. First thing we want to do is we want to isolate our trig function. So let me go ahead and divide both sides by 3 here, and that goes away. And now I'm left with the tangent of 3x is equal to the square root of 3 over 3. All right? Now, we can go ahead and state, okay, tangent of 3x equals to the square root of 3 over 3. Well, here we can call this thing u. Again, that's not necessary if you can keep this part straight in your head, but for the first few examples, it's a good idea to give this a try. As you get more used to it, you kind of do that step in your head. So here we're going to say let u be 3x. So here I'm going to write this as the tangent of u equals root 3 over 3. Okay, but now I want the tangent of something, that's the root 3 over 3, and that's pi over 6 radians. So here, that gives me that u is equal to pi over 6, just like that. Now remember, the tangent function is, just like every other trig function, periodic. Here I'm going to go ahead and sketch the graph of the tangent function to remind ourselves of what that looks like. Here, we note that if we want the tangent of a number to be root 3 over 3, in that central period, there's only one number that does that, right? There's only one x value for every y value. It's a one-to-one function. Okay, but at least in this interval here. Okay, so that means that in this interval, there's only that one solution. But keep in mind, this is periodic. And since the period length of the tangent function is pi, that means every time I add a multiple of pi, or in other words, I say plus n pi, then that's going to give me another solution in a different period of tangent. So here, if u is equal to pi over 6, adding any multiple of pi would give me another solution. But u is not just its own separate variable, u stands for 3x. So now I could substitute that back in. Instead of saying u is equal to this stuff, I can say 3x is equal to this stuff. Just like that. But now I'm trying to solve for x, so here I can divide by 3, and divide by 3. So this will give me just an x all by itself. Here I have pi over 6. I'm dividing by 3. Remember, dividing by a number is the same as multiplying by its reciprocal, so that's the same as saying times 1 over 3, and that'll give me 1 pi over 18. So here that's going to give me pi over 18 plus n pi over 3. And here we're not going to go through and plug in values of n, because here we're not looking for any specific solutions between any two endpoints. We're not looking for solutions in an interval. We're just saying we want every possible solution. And here, this is every possible solution. If you now wanted to find solutions in an interval, you can start plugging in different values of n, and you would get as many as you need. But that is our solution set. The way these problems can become more complicated is if you have a multiple angle, if you have an angle that's something different than just x, if it's 2x or 3x, but that is different in different parts of the problem. So for example, let's say we had cosine of 2x, so here I'm going to solve. The cosine of 2x minus the cosine of x is equal to 0. Because they have different arguments, if I try to substitute, if I say let this be u, well then that's not u. If I say let this be u, well then that wouldn't be u. So my substitution, my u equals to something, in this case u equals to 3x, isn't really possible here. And if it's not really possible, then we're going to have two separate things to worry about. So how do we do this? Well, we have several identities that involve different arguments. We have half-angle formulas and double-angle formulas for sine and cosine. We have sum and difference formulas. So we can use some of our identities to rewrite some of these expressions with a different argument. For example, here, the cosine of 2x, well, I can use a double-angle formula. Here, let's go ahead and recall that. We have a couple of double-angle formulas. We have the sine of 2x, that's equal to 2 times the sine of x times the cosine of x. And we have the cosine of 2x, which is equal to, and there's a few ways you can write it. You can write it as cosine squared of x minus sine squared of x. Personally, that's the one that I remember the easiest because it almost looks like a Pythagorean identity with a minus instead of a plus. But there are other ways you can write that. You can write it as 2 cosine squared of x minus 1, or there's 1 minus 2 sine squared of x. So now here, what I want to do is I want to write this expression so that I don't have a double angle. Okay, so it would be one of these. Cosine of 2x could be any of these. Now, I notice that here, once I get rid of this one, or rather, change this one, I'm going to have minus cosine of x. So since I have 3 different choices, I think I'd rather choose this middle one, because this top one and this bottom one both involve sine of x, but this one only involves cosine of x. And the fewer things that I have to worry about, the less work I'll have to do. All right? So here, I could use any of them. They all are valid. But by using this one, I'll only have to worry about cosine of x and cosine squared of x. No sines or anything like that. So here, let me take cosine of 2x and replace it with 2 cosine of x squared minus 1. Right? So that became this. And now I still have a minus cosine of x is equal to 0. This one came down. And this one became these two because of our identity. All right. So now, let me rewrite this in descending order. This almost looks like a polynomial. I can write this as 2 cosine squared of x minus cosine of x minus 1 is equal to 0. And now that really looks like a polynomial. So let me write it with a substitution. Here, I'm not going to substitute the angle anymore. The angles are just x. The angles aren't going to be a problem anymore. So what I've done is I've exchanged a problem with a multiple angle for something with a bigger power, but with the same angle. And these we saw how to solve in the previous section. Here we can think of this as 2u squared minus u minus 1 equals to 0. Here we're just saying, okay, the cosine of x, we're calling that u. All right, so let u equal the cosine of x. So that's 2 cosine of x squared, that's 2u squared, minus the cosine of x is minus u, and then the minus 1 and equal 0 are going to stay the same. Well, now this, we can go ahead and factor. This will factor as 2u and u like, that's the wrong sign. There we go, plus 1 is equal to 0. So this factors out as 2u plus 1 times u minus 1. Now, we have the product of two things is equal to 0. That means either the first thing is equal to 0, 2u plus 1 equals to 0, in which case I could subtract 1 to the other side, 2u is equal to minus 1, and I can divide both sides by 2, which is minus 1 over 2. On the other side, I could say, well, if u minus 1 is equal to 0, I could add the 1 over to the other side, and that'll give me u equals to positive 1. But remember, u, up here, we said u was equal to the cosine of x. So this is now the cosine of x equals to negative a half. And the cosine of x is equal to 1. This one here and this one here. Well, now we know what both of those are. We can look on the unit circle for that. I'm looking for, on the unit circle, the cosine of x is equal to negative a half. That'll be 2 pi over 3 and 4 pi over 3. And I'm looking for where cosine of x is equal to 1, and that's over here at 0. All right, so I have 3 different solutions there. I have x is equal to 2 pi over 3. I have x is equal to 4 pi over 3. And I have x is equal to 0. But again, here we want all possible solutions. We're not restricting ourselves to any interval. So here we know that the cosine function that we just solved for here has a period length of 2 pi. So here I can write this as plus 2n pi, plus 2n pi, plus 2n pi. Here you don't have to write the 0. After all, anything plus 0 just stays itself. But in any event, here we have our 3 families of solutions. Here we have an infinite number of solutions, but all of those infinite number of solutions fall into one of these 3 categories. And there we go. This is the solution to our equation. All right, so let's take a look at another example. Let's consider now we're going to go ahead and solve the equation sine of 2x is equal to 2 times the cosine squared of x. Not in any interval, just any solution we can find. So go ahead and pause the video and give it a try. Work through it, and once you get an answer, go ahead and unpause the video and we'll go through it together. All right, so let's take a look. Here we have 2 different arguments, x and 2x, and we don't want that. We want to have just a single argument. So we have a double angle formula for sine of 2x, and that's 2 times the sine of x times the cosine of x. is equal to 2 times the cosine squared of x. Here I've changed this side with the double angle formula. Here I've left that alone for now. Okay, now I'm going to go ahead and move all this stuff over this way. I want one side to equal to 0. Okay, so I'm going to write that as 2 cosine squared of x. Let's see, minus 2 sine of x cosine of x, just like that. Now, one thing I notice is that I have the cosine of x as a common factor here. I also have a 2 as a common factor, so I can factor these out. I can take these 2's and factor them out, and each of these has a cosine of x as a common factor, which I can factor out as well. If I divide this by 2 cosine of x, I'm just left with cosine of x. Minus, if I divide the 2 and the cosine of x, I'm just left with the sine of x. Looks like that. But now I have the product of two things, and that product is 0, which means either the first one is 0 or the second one is 0. So I can write this as 2 cosine of x is equal to 0. Here I divide both sides by 2, which will just give me cosine of x is equal to 0. On this side, I have cosine of x minus sine of x is equal to 0. And if I add the sine of x over to the other side, I get cosine of x is equal to negative, that's equal to positive sine of x. And I can solve both of these. Cosine of x is equal to 0. That's going to be at pi over 2 and 3 pi over 2 on the unit circle. The places where cosine of x is equal to 0 on the unit circle are pi over 2 and 3 pi over 2. Here, I want to find the places where cosine of x and sine of x are equal to each other. Well, there's two places where that happens. At pi over 4, both the sine of x and the cosine of x are root 2 over 2. And over here, at 5 pi over 4, the sine and the cosine of x are both negative root 2 over 2. So at both of these places, we have the sine and the cosine of x are equal to each other. So I have x is equal to pi over 4, and I have x is equal to 5 pi over 4. And of course, we're not looking for any solutions in particular. We're looking for any and all possible solutions. So here, all of our functions, sine and cosine, all have the period of 2 pi. So every time I add 2n pi, every time I add a copy of 2 pi, that gives me another solution. So by writing plus 2n pi for here, n is any integer, that'll give us every possible solution to that equation. And here there are an infinite number of solutions, but they all fit into one of these 4 categories. And there we go. All right. As our last example, we're going to take a look at one that is numerically just a little bit messier. It's going to work the same way as this does, but again, just the numbers are going to be slightly messier than any of the examples we've had so far. So let's go through this one together. Here we're going to go ahead and solve in the interval from 0 to 2 pi. So we're only looking at the interval on the unit circle. All right, so the equation is going to be 2 minus the sine of 2 theta is equal to 4 times the sine of 2 theta. Now, one thing to notice here is that both of these are the same angle. So in this case, we kind of have a choice. We could convert everything back using the double angle formula, or we can just leave things and combine like terms. Combining like terms seems like it might be a little bit easier, or maybe not. But here, let's give it a try. So I'm going to go ahead and add the sine of 2x to both sides. Whatever I do to one side, I can do to the other. Add the sine of 2 theta to both sides. This is now 0, and I'm left with just that number 2, equals 4 sine of 2 theta plus another sine of 2 theta would give me 5 sine of 2 theta. Just like that. Here, this starts to look familiar. This starts to look like some of the earliest problems that we had. So here we can divide both sides by a 5 to isolate our sine function. So here this is gone, and we're left with, let me write this over here on this side. Well, no, that's fine. I can leave it like that. I can write that as 2/5 is equal to the sine of 2 theta. Okay. Now, at this point, again, we have the option. We could use the double angle formula, but in this case, we can just take the sine inverse. Now, the third option, of course, is you could look on the unit circle and try to find the sine of something is equal to 2/5. Oh, no, that's not really an option. 2/5 is not a number that shows up on our unit circle. So that's not going to be a nice number. But what we can do is we can take the inverse sine of both sides. So here I can say sine inverse here. And over here I can say sine inverse here, and that is perfectly valid. I can take the sine inverse of 2/5 because 2/5 is in the domain of the sine inverse function. Remember, the sine inverse has a domain that's what? Between -1 and 1? Yeah, between -1 and 1, which that most certainly is. So here, the sine inverse of the sine of 2 theta will just give me 2 theta. So let me write that down. 2 theta is equal to the inverse sine of 2/5. Now here, I'm going to say plus 2n pi. I know that I don't want every solution. I just want the solutions that make this, that make this equation true in between 0 and 2 pi. But here I'm about to divide. So that means that some solutions that otherwise might not have fit, that were further along rotations of our unit circle, might now fit. So here, I'm going to go ahead and write it this way. And now I can go ahead and divide both sides by 2. So this will give me theta is equal to 1/2 times the sine inverse of 2/5 plus the 2's are gone, so that's n pi. Okay, well, I want something between 0 and 2 pi. Okay, well, that's a positive number here. So a positive number plus pi, and then a positive number plus 2 pi. Oh, well, that's not going to be good, because if it's just 2 pi plus something is already bigger than 2 pi. So here, I can use the original number. If I say, okay, let's let n equal to 0, that's going to give me 1/2 sine inverse of 2/5, just like that. If you're a little uncomfortable with that number, that is the precise number, but let's go ahead and take a look and see what it is just as an estimate, just so that you can confirm that it is in fact between 0 and 2 pi. Remember, 0 is 0, and 2 pi, that's, 2 times pi. That's 6 point something or another, yeah? So here, that's 6.28 something, like that. Okay, so if I took 2/5, 2/5, there we go, and I took the inverse sine of that. Oh, my apologies. My calculator's in degrees. This whole thing's supposed to be in radians. We're doing everything in radians here. If I take 2/5 and I take the inverse sine, I get that number. And then if I multiply that by 1/2, I get that number. And that is definitely between 0 and 6.28 or whatever. Yeah? Okay, now, if I let n equal to 1, that's going to be 1/2 sine inverse of 2/5 plus, well, that's going to be 1 pi. Okay, so there's my number that I had before. Let's see what happens if I add pi. And that's 3 point something, which is also definitely between 0 and 2 pi. So both of these are perfectly good answers. But notice, if I add another pi, If I said, let me let n equal to 2, here I don't even need the calculator to confirm that. That's going to be a positive number plus 2 pi. If I have a positive number plus 2 pi, that's going to be bigger than 2 pi. Sure enough, if I add another pi, that's 6.4 something, which is definitely not between 0 and 6.28. So here, that one is definitely not valid. It is a solution, but it is not in our interval. And so these are our only solutions. All right? Keep in mind, n is an integer. It could be negative. But again, we run into the same problem we had over here. N could be -1. But if we did that, that would be 1/2 times the sine inverse of 2/5. And that would be -1 times pi. So that would be minus pi. And again, that would be not in our interval. Because this right here is a positive number, but it's a very small positive number. The inverse sine of 2/5 times 1/2 is a very small positive number. And if I subtract pi, that's going to give you a negative number. And again, I don't want a negative number. I want it between 0 and 2 pi. So again, this one is too small. And this one is too big, which means these are the only ones that are just right. Right? Today's math lesson brought to you by Goldilocks and the Three Bears. Huh? So we have our only solutions in the interval from 0 to 2 pi. And our solutions are theta is equal to 1/2 sine inverse of 2/5. And theta is equal to 1/2 times the sine inverse of 2/5 plus pi. And these aren't families of solutions. These are just the only two solutions in that interval. All right? So that is it. All right, so that's it for this section.